Hello everyone, and thanks for joining me. In this video lecture, we're going to start Module 3, which is going to cover a series of continuous random variables. We're going to introduce continuous random variables first, and then we'll get to specific distributions such as uniform and normal. So an introduction to continuous random variable is what we're going to do first, and you can learn about this in the textbook in sections 4.1 to 4.3. So the main feature of continuous random variables is that it includes an interval of real numbers and is uncountable. So if you have a random variable that has a range between 1 and 5, any number between 1 and 5 is a possibility for that random variable. And there are uncountable number of possibilities essentially between 1 and 5 in terms of real numbers. Examples would be, life of a transistor. And when we're talking about life, we're essentially referring to time, and time is continuous. Between any two values of duration time, there are millions other values. So there are uncountable possibilities for life of a transistor because the range in time is continuous and non-countable. Again, time between customer arrivals, it's a nature's time, and time is continuous. And also a pH level of a water sample. In pH values, between any two values, you have so many other real numbers. So these are continuous random variables, some examples. We'll look at more examples in this module. Let's get started on how can we calculate probabilities associated with continuous random variables. And in order to do that, we gotta have the probability density function, or PDF. Probability density function is equivalent of PMF, but for continuous random variables. You remember in discrete random variables, we had probability mass function, or PMF, which we used to calculate probabilities. Here, the same concept is called probability density function, or PDF. The properties of PDF is that it's non-negative because probabilities of any random variable cannot be negative. You don't have a probability of negative 20%. So it's got to be non-negative. Also, when you add up the probabilities in the range of that random variable, it should add up to 1. Or 100%. And that's what we learned about in discrete random variables as well. If you want to calculate probability of a random variable x being between two values within its range, you have to integrate over the PDF function from a to b. And this is something that is different in continuous. You have to integrate. In discrete random variables, if you were to calculate this probability, you would have to add up probabilities of possible numbers between these two range and just add them up. It would be countable. You could, calculate probability of x equals to a plus probability of x equals to a plus 1. And you add them up until you get to probability of x equals to b. And this was the case in discrete distributions, because between a and a plus 1, there is no other possibility. But in continuous, you cannot do that. So what you do is you integrate from a to b, because there are uncountable number of possibilities between a and b, so you got to integrate. So let's get that a little more graphical here. So here you can see a PDF function basically. On the x-axis, you have the x, or the values that random variable can get. And on the y-axis, you have f of x, or PDF, which represents the probabilities. If you want to calculate probability of x between a and b, and a and b are two values within the range of this random variable. This is the range of this random variable. You have to integrate from a to b over the PDF function. And that integration essentially gives you the area under the curve. And that represents the probability of that random variable being between a and b. Since that's how we calculate probabilities for continuous, if you only calculating probability of x equals to any number, and I want to emphasize here on that equality sign, if you're calculating probability of x equal to any number, that probability is 0 for continuous random variables. Because let's say that this is that point, right? It's point x, let's call it. It's the same x that we have here. There is no area under that single point. So that integration would be equal to 0. So that's why for any specific point, probability of x equals to that point is always equal to 0 for continuous. And because of that, there is no difference between probability of x, less than equal, x2 more than equal x1, or just saying, less than equal x2 more than x1, or more than equal to x1, less than x2. So all of these are the same, because by adding a specific point, like x2 or x1, we're not adding to the probability. So you can just, be relaxed in continuous cases and don't worry about these, equality signs. You can just, leave it as less than or more than, because it doesn't make the probability change. We're going to look at a multiple number of examples in the next video.